Scattering at rough surfaces is a central topic in both nature and ethology, as can be seen, for example, in the propagation of ocean waves in a rough seabed, or the scattering of acoustic waves off the walls of a concert hall. A description of all these different phenomena relies on the surface scattering theory, which predicts how a specific surface profile scatters an incoming wave into a given outgoing direction. As we show in our manuscript, the central problem of physics and engineering is solved only incompletely with all existing techniques that are conventionally used for this purpose. To show this deficiency, we investigate the transmission of waves through surface-ordered waveguides with a step-like surface profile, a situation that is well studied in literature. Using numerical as well as analytical techniques, we observe resonant enhancements of wave reflection in the system, which are due to higher order effects in a disorder that were previously neglected in earlier studies of the same setup. These reflection resonances are very robust and pronounced in their amplitudes and provide clear evidence for the incompleteness of conventional techniques. For the systems at hand, we managed to provide the missing expressions fully analytically, such that we can formulate a well-defined condition for the resonances to appear, leading to a quantitative agreement between numerical and analytical results. In the following, I will now explain this in more detail. The key quantity in the description of transmission for waveguides is given by the surface profile function psi, highlighted here in gray. Waves that are injected into such a waveguide are reflected back to the input port by two competing scattering mechanisms. The conventional scattering mechanism, already known in literature, is of the order of the reference strength sigma and contains contributions of the amplitude psi and its derivative, therefore named the amplitude gradient scattering mechanism. The new scattering mechanism which we take into account is independent of the conventional one and stems from the square of the gradient of psi, giving rise to the so-called square gradient scattering mechanism. In previous studies, this mechanism was neglected, since it is proportional to the square of the reference strength of the profile boundary, while the amplitude gradient scattering mechanism is of lower order. Neglecting the seemingly small square gradient scattering contribution is, however, generally not justified. To show this explicitly, we numerically simulate wave transmission for a waveguide with a step-like surface profile, as depicted at the top, with step width delta and y width d, where we allow for two open modes which are injected from the left. Numerically, we calculate the total alternation length of a given mode. I show here the inverse alternation length of the second mode as a function of the step width delta, which gives a measure for this mode's reflection in the system. On the top left, we display an example of a scattering wave function calculated at the tip of the green curve, highlighted in gray. The wave function can be seen to extend over the whole system, corresponding to a particularly small value of the inverse alternation length. Comparing the numerical data for the inverse alternation length to the conventional amplitude gradient scattering mechanism, shown in blue, we immediately see that this theory alone fails to predict the correct behavior. Especially the one order of magnitude enhancements in the reflection are missing, indicated here by black arrows. Directly at such a resonant value, the back reflection is greatly enhanced. This can be seen nicely in the wave function plot above, where the wave function is evaluated at the peak of the green curve, highlighted in gray. Going back to the inverse alternation length and overlaying the predictions of square gradient scattering separately, we see that the deficiencies of amplitude gradient scattering can be understood to come exactly from this additional higher order contribution. Finally, adding up both expressions for the inverse alternation length and comparing them with our numerical data, we obtain excellent quantitative agreement. Since we can describe our model fully analytically, we can also identify the position of the reflection resonances, as being determined by the condition that the product of the step width delta and twice the longitudinal wave number is an integer multiple of 2 pi. In our paper you will find all details on how we arrive at this result, including a detailed analytical treatment of all the involved scattering mechanisms. I thank you for watching this video and cordially invite you to have a look at our paper.